All right, well, why don't we start? So welcome to the Oxford Lectures on the Philosophy of Mathematics. I'm Joel David Hampkins, and this is week 4, and the topic is geometry. I want to start, of course, by talking about classical Euclidean geometry. It's probably an ageless paragon of deductive mathematical reasoning. Of course, it's aiming to elucidate the fundamental truths of geometry, the mathematics of space. And Euclid starts with points and lines as primitive notions, and he has 10 axioms. There's 5 essentially algebraic common notions and 5 essentially geometric postulates. And then he proceeds to build this monumental edifice, proving one statement and then another and then another. And in doing so, he taught us all the axiomatic methods. So he showed us how to do mathematics. And not only did he show us how, give us a method for doing mathematics, the axiomatic method, but also an unequaled example, namely Euclid's Elements, which of course was the most successful and influential textbook ever written. And it was the principal mathematics textbook for over 2,000 years. Okay, so let's just talk a little bit about his methods. So he has 2 classical construction tools, the straight edge and the compass. So the straight edge is given any 2 points, then you can construct the line that joins them. And a compass is this device like a V-shaped thing, and you put 1 point at the center and 1 point on and the other tip of it at another point, and you can make a circle with the given center and containing the given point on the edge. So you can construct a circle with a given center and radius. Okay, so these 2 tools suffice for all of the applications that are given in Euclid's Elements. And I want to just show you, for example, how to do that. So let's just construct the perpendicular bisector of a line segment. So we're given 2 points, A and B, and we want to construct the perpendicular bisector on the segment from A to B. And so what you do is, first of all, you pick this point as the center of a circle, and you make a circle that looks like, that contains this point. So this is part of a circle, and then you do it the other way. So using this point, you use your compass to make a circle going like this, and you get these 2 intersection points. Yeah? And then using the straight edge, you can draw a line connecting them. If I had these large geometry tools for using on the chalkboard, I would have them here. And I'm sorry I don't have them. But I hope we can understand it anyways. Okay, so we built this line here and this point here. So if this was the point A and this is the point B, and this is the point P and this is the point Q, then we've constructed the midpoint C of the line segment AB, and this line here is perpendicular to AB. Okay, this is called the method of Apollonius. It's not actually how Euclid proved how to construct the perpendicular bisector, but let's talk about that a little bit. First, I want to say, well, to construct the perpendicular bisector is not quite the same thing as to prove that it is the perpendicular bisector. So let's give an argument for that. So why is this point the midpoint? Why is this line perpendicular to AB? And for that, what we can do is we can use these other triangles here. Let me draw them in yellow. So I'm going to make that triangle, and I'm also going to make this triangle. And each of those yellow lines, if you think about it, is the radius of the circle. Because, for example, this line is the radius when we had center A, yeah, and this line is the radius when we had center B. Yeah. So each of these lines is congruent to each other because each of them is congruent to the segment AB. And now, if we think about this this large triangle here, so QAP, you know, then and in comparison with this large triangle here, yeah, then those 2 triangles have all congruent sides. So that these 2 sides are congruent to these 2, and they have the same base there. And so therefore, by side, those 2 triangles are congruent. And from that, it follows that this angle is the same as this angle, because congruent, the associated parts of congruent triangles are also congruent. Okay, and now if we think about this triangle here and this triangle here, then they have the same angle here and the same hypotenuse, the same side, and this side is also common. So by side angle side, those 2 triangles are congruent. And from that, it follows that this side is congruent to this side. So therefore, C really is the midpoint of AB. But secondly, we also know that this angle here is congruent to this angle by the congruency. And therefore, they add together to a straight angle. So therefore, this is a right angle. So therefore, we found a perpendicular bisector of AB. Okay, so that's basically a proof using those triangle congruence theorems of side, 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 and side angle side. Now, maybe if you studied geometry in high school, then you might have seen the sort of two-column proof format, which is very common, particularly in 20th century American schools. Then you make a proof by making a list of geometric statements in the first column, and if for each statement you have a reason why it's true in the second column, and there's only certain reasons that are allowed. And this is a very common style of undertaking geometric proof, but it's not at all Euclid's style. If you read Euclid's Elements, then it's written in a sort of open prose style. It's quite readable even today. I mean, in translation, of course. So it's not in this two-column proof style. This is a very recent innovation. Okay, now I'd like to talk about maybe how contemporary geometers think about this fact. For example, that if you do the Apollonius construction, that it gives you the perpendicular bisector of the original segment, because they wouldn't necessarily feel required to undertake a proof by straightedge and compass in that style using the Euclid's theorems. Rather, to see, for example, that line segment PQ is perpendicular to AB, then we could consider the symmetries. For example, given a line segment AB, then consider the reflection through the actual perpendicular bisector, the reflection of the plane through the actual perpendicular bisector, whatever that bisector is. That reflection is going to swap A and B. And therefore, it will take those circles to each other. So therefore, it will fix the points P and Q. So therefore, the reflection on the actual perpendicular bisector doesn't move the points P and Q. So therefore, the points P and Q must be on the line that is the perpendicular bisector. So this is a more abstract way of arguing. Instead of about the details of the construction, side angle side, and all of that, we can just see abstractly by symmetry that PQ must be the perpendicular bisector on those grounds. So that way of thinking really leads to Felix Klein's Erlangen program, by which you study a geometric space by means of the group of transformations and invariants that it gives rise to. So geometric properties are precisely those that are preserved by those transformations of the space. So in the Euclidean plane, for example, well, we have translation, we have rigid translation. You know, you can move figures around in the plane. We also have rotation, so you can rotate figures in the plane, and we have reflections. And in fact, any one of those three kinds of transformations of the plane can be achieved by at most 3 reflections. So you really only need reflections to generate all of those symmetries. And so those 3 transformations, of course, preserve distance. They're preserving the metric properties of the plane, and therefore the congruence notion that comes from that group of symmetries of the plane is going to be distance preserving. But if you want a different kind of geometry where you're not required to preserve distance, for example, if you allow scaling of the plane, then the congruence notion that you're going to get from that group of transformations is going to include similarity. It will be similarity. 2 figures will be congruent with respect to that concept of geometry, just in case they're similar rather than actually the same size. So, for example, you could also study the group of transformations of the plane by not allowing reflection. So this would be a kind of orientation preserving notion of congruence. So 2 figures would be congruent in that concept of geometry, just in case you can rigidly translate one to the other by translation and rotation, but not allowing reflection, which is not orientation preserving. Okay, so ultimately that perspective leads you to a picture of geometry by which you specify a geometry really by specifying a group of transformations. And then a concept counts as geometrical exactly when it's a concept which is preserved by every transformation in that group of transformations. It's a much more abstract way of thinking about what a geometry is. All right, let me return to this classical case now, though I want to discuss a certain controversial issue in the use of the compass. So if we think about how a compass is used, so maybe we have a line segment AB here. We know the compass enables us to build a circle around A, but the way a compass is often used is that you measure the segment AB, with the compass, and then you pick the compass up and you put it down over someplace else at some point C, and you make a circle of that radius over at that other point C. So what we really want to do is, well, we know how to build the circle with radius AB, but what we want to do is build a circle of that same radius over here at this other point C. And the question is, are we allowed to or not? Because of course, cautious geometers in Euclid's day objected to this use of the compass, because the axiom, the postulate about the use of the compass doesn't say for any line segment and for any other point somewhere else you can make a congruent circle. It just says for any point to be used as the center and any point specifying the radius, then you can make the circle with that center and that radius. So this sort of picking up the compass and putting it over there isn't allowed according to the axiom. And so so some people built special compasses, that collapsible compasses, so that they work, but only when they're under some slight pressure. So you have to be pushing down on them in order for them to hold the distance. And as soon as you pick them up, then the pressure is lost and they kind of fall apart. They lose the distance. So you can't pick it up and put it over there. And the question is a rigid kind of compass that where you can do the measurement and pick it up and move it, is it equivalent constructively to this collapsible compass? And in fact, it is, and Euclid proved that it was. This is called the compass equivalence theorem, the compass equivalence theorem. So any construction that you can do using what I view as an ordinary compass that holds its distance, you can also achieve it with a collapsible compass. So let me prove that. I'm going to give one proof, but then I'm going to give you a reason to not like my proof and to prefer maybe Euclid's proof. So if I have 3 points A, B, and C, and I want to construct this circle, then what I'm going to do first is use the straight edge to make a line that connects A and C. And then I can use the compass to make this circle. But also we saw how to make a perpendicular. So I can make a perpendicular at A, perpendicular to the line AC. So I can make this line perpendicular. And therefore I can find this intersection point. And now I can make another perpendicular here, all the way over here. And I can make a perpendicular at C going up. And I can find this intersection point. And then that line segment I can use to make a circle. And the point is that because this is perpendicular and this is perpendicular and this is perpendicular, it's therefore a rectangle, and therefore this length is congruent to this length, which is congruent to AB. And so I've done it. Okay. So now there's 2 reasons to not like this argument that I just gave you. So this is a proof of the compass equivalence theorem in Euclidean geometry. But one reason not to like it is that I also use the straight edge. I didn't do it just with the compass. And so the argument doesn't show that this kind of compass is equivalent to a collapsible compass just by itself. I needed the straight edge. But the second reason to not like this proof is that I'm using Euclidean geometry. I'm using the parallel postulate. In order to build this rectangle, I'm really using the 5th axiom, which we're going to talk about later when we talk about non-Euclidean geometry. But this argument just doesn't work in non-Euclidean geometry because I'm using these right angles and the fact that I made a rectangle. Okay, but meanwhile, Euclid gives us a proof that doesn't use a straight edge and doesn't require the parallel postulate. And it's using only circles. So he builds, I don't know, half a dozen circles, and then you can show that you can build that other circle on the other side. Okay, so that's the compass equivalence theorem. Now I'd like to think about what's going on with these constructions. So let's talk about the universal construction procedure. So, if I start with 2 points A and B, then the question is, well, what can we construct from A and B? And what I want to do is systematically do perform all possible constructions using straight edge and compass. So if I have 2 points A and B, well, then at first I can make a line that joins them, okay? And then secondly, I can make 2 circles, one centered at A and containing B, and one centered at B and containing A. So this circle is going to be something like this, and then the other circle is going to be something like this. I'm sorry, my diagram is not perfect. So I got to make that better. I'm sorry. This circle is just not good enough. It's too small, I guess. Okay, so let's make it better. I should have, yeah, okay, oh my gosh. Is that better? Okay, maybe. So, all right, now when I did that, I did my straight edge as much as I could, and I did as many circles as I could draw using just those 2 initial points. And what we find are more points. We got this point here, and this one, and this one, and this one. So that gives us now 4 new points, and we have 6 points altogether. And now we can start drawing lines and circles using those 6 points. So I could make this line, and I can make this line, and I can make this line, and so on, and this line. There's a lot of lines. And I can make all possible circles using those 6 points. And if you make a diagram, you draw all possible lines and all possible circles using those 6 points, then, and you look at the intersection points, then you get 203 points. So it's this mess of a picture with a lot of circles and lines in it. Okay, so the sequence so far is, we started with 2, and then we had 6, and then 203 points are arriving next. You can start to see some of those points here that are intersecting. So when I drew some of those lines and some of the circles, for example, there's going to be a circle here. So we're going to have more points coming from up there and so on, in those 203 points. So we could imagine carrying out this universal construction process and systematically generating all possible points in the construction. And okay, if we take these 203 points, well, I was wondering a year ago when I was first thinking about this, how many points and lines you would get and circles you would get at the next stage after that. And I knew it would be quite a lot. For example, if you have 203 points, then basically you have over 40,000 pairs of points, and any 2 points are going to determine a line. Some of those lines will be the same, and any 2 points determine 2 different circles. So that's giving us some upper bounds of 40,000 lines and 80,000 circles that we could construct at the next stage. And so I knew that to count them, of course, the 203 points I could count by hand, but if I have 40,000 points, then I'm not going to be able to really count that by hand. And also I'm not going to be able to use computer algorithm to count them either if I'm using just floating point approximations, because maybe 2 points are very, very close together, and I need to detect whether or not they're exactly identical or whether they're just very, very close to within my round off error. And so I need to be performing sort of exact calculations. And so I posted this question on Math Overflow, and we got some answers. So Pace Nielsen found that the 203 points formed exactly 17,562 distinct lines and exactly 32,719 distinct circles. But he didn't know how many intersection points all those lines and circles had. And then it was someone here in Oxford, a graduate student, Teofil Camarasu, found that when you intersect all those lines and circles, and you perform exact calculations, not approximations with roundoff, so there's no roundoff in these calculations, you get exactly 1,723,816,861 distinct points of intersection. And that calculation took 6 continuous days of computer time running on 6 different processors on 3 different machines. So it's really quite an intense calculation. Okay, so the next number on the sequence is, what did I say? 1,723. Oh my God, 723,816,000, and then 861 number of points. Okay, and then you do it again, right? This sequence never stops because all of those points, any 2 of them determine a line, and any 2 of them determine 2 different circles, and we would want to construct all those lines and circles and intersect and so on. This is the universal construction sequence. And And at each stage in the construction, we're producing finitely many additional points. And every constructible point will arise at some stage in this process, right? No matter what construction you're doing from those initial 2 points, eventually, if we're doing all possible constructions, we will have done your construction. And therefore, every constructible point, every point that you could construct by any process will appear at some stage in this universal construction process. So Descartes had a really great idea. So what he proposes that we should look at the line and start with 2 points, and let's call them 0 and 1. We think of them as specifying a unit distance, And then the question is, which numbers, if we think of every point on this line as a number, the number line, then which numbers can we construct by the classical geometric construction methods of straight edge and compass? Of course, I can immediately construct the number 2. If I use 1 as the center of a circle, then I can construct the number 2. And therefore I can construct 3 and 4 and so on, Also, I can find midpoints, so I can construct 1/2 and 1.5 and so on, all these points in between. I can also construct the square root of 2, because I can, on this unit interval, I can construct a square, and the diagonal of that square has length square root of 2, and then I can use a compass to bring it down here, so I can construct square root of 2 on the number line. So there's quite a lot of numbers that I can construct. So a number is said to be constructible by straight edge and compass if you can find a point on the number line. Using straight edge and compass, you can construct a point on the number line whose distance from 0 is exactly that number. Okay. So, of course, one might ask, well, maybe every number is constructible. Are there any non-constructible numbers at all? And one easy way to see that there must be non-constructible numbers. Let's first give a soft proof, which is not the original proof that people had for this fact, but there's a soft proof. And it follows just by considering the universal construction sequence. We already described how to generate all the constructible numbers just by systematically carrying out all possible constructions. But the point is that at each stage in that process, we're only adding finitely many additional points. So therefore, the constructible points, the constructible numbers, are obtained by a countable sequence where we're adding finitely many points at each stage, and therefore there's only countably many. So by Cantor's argument, there must be some points on the number line that are not constructible because there's uncountably many points on the number line, but only countably many constructible points. Okay, so that's a kind of Cantor-style soft proof of the existence of non-constructible numbers. But in fact, this fact was known before Cantor, well before Cantor, using some quite deep ideas in mathematics. So let's discuss that. Let's think about the nature of constructible points. So whenever you're adding a new constructible point, it's because you were intersecting 2 lines, or you were intersecting a circle with a line, or intersecting 2 circles. So in each case, it's because you're solving a quadratic equation, because the circles have quadratic equations, x squared plus y squared equals r squared, or if you translate it to a given center. So there's a degree 2 polynomial equation that you're solving for each of those intersections. And so it follows that whenever you add a new constructible point, that point will fulfill a degree 2 polynomial over the previous points that you had. And therefore it follows from that the algebraic degree of the constructible points must always be a power of 2, because each time it's a quadratic over what you had before. Either you already had it, or else it's going to be degree 2 over what you had before. And so every constructible number must have order 2 to the n for some n over the rational field. So therefore, if I have a number that doesn't have order 2 to the n, degree 2 to the n, then it can't be constructible. So let's use that in connection with some of the classical non-constructibility problems. So one of the classical construction problem was given a line segment AB, then we think of that line segment as determining a cube, and I want to make a line segment whose cube has exactly twice the volume. Okay, so I want to make another line segment over here, CD. So given AB, I want to make a line segment whose cube has exactly twice the volume. This is called doubling the cube, you know. And basically, if this distance is 1, then this cube should have volume 2, because this is 1 by 1 by 1, has volume 1. So this one should have volume 2. So each side should be the cube root of 2. You know? But if x is the cube root of 2, then x cubed minus 2 is 0. So x is solving this irreducible cubic polynomial. It doesn't have degree 2 to the n for some n. And therefore, the number cube root of 2 is not constructible by the reasoning that we gave earlier. So this solves a problem that really stymied mathematicians for hundreds of years, well, almost 2,000 years. And it uses this theory of algebraic extensions of the rationals and the degree of roots of polynomials and so on. It's quite sophisticated mathematics. Let's look at another example, the problem of trisecting the angle. So the problem is, given an angle, you know, so we're given a point and then 2 other points. So what we want to do is construct a trisection so that this is exactly 1/3 of the angle, you know, and the question is, can we construct a point which is going to realize that trisection? Now, of course, sometimes we can. For example, if the original angle was a straight angle, then the trisection is 60 degrees, but we can construct a 60-degree angle because that's what the Apollonius construction provides. Those triangles that I drew in that proof, the first proof we did, those were equilateral triangles. They have 60-degree angles. So I can construct a 60-degree angle. Also, if you start with a right angle, then the trisection of that is a 30-degree angle, but you can also construct a 30-degree angle because you're just bisecting a 60-degree angle. So therefore, sometimes you can construct the trisection of an angle. But let's consider whether you can construct, say, the trisection of a 60-degree angle. So you want to build an angle of 20 degrees. Okay. But it turns out that if you could trisect a 20-degree, I mean, if you could trisect a 60-degree angle and make an angle of 20 degrees, then you would also be able to construct the cosine of 20 degrees. That's the length. If you have a unit circle and the angle is 20 degrees, then if you project onto the horizontal, you're going to have cosine 20 degrees. But it turns out that if x is cosine of 20 degrees, then 4x cubed minus 3x equals 1/2. Just follows from basic trigonometry and the triple angle formula. And therefore it has degree 3, not a power of 2. And therefore you cannot construct the cosine of 20 degrees. And therefore you cannot construct an angle of 20 degrees. And therefore you cannot necessarily trisect an angle. So here's another example, squaring the circle. So given a circle, construct a square with the same area. So a circle is specified by the center and a point on the edge, the radius. Yeah. So given a line segment, thinking of it as determining a circle, construct a square, meaning construct a segment who's such that if you build a square on that segment, it would have the same area. Yeah. But of course, if the original segment had length 1, then the area of the circle would be pi. And so what we really want to do is construct the square root of pi, because the square whose side length was the square root of pi would have area, the square root of pi times square root of pi, which is pi. So to square the circle, you would have to construct the number square root of pi. But the square root of pi is a transcendental number. It doesn't satisfy any algebraic equation at all over the rationals, and therefore it's not constructible. That's a deep fact, though. I mean, to prove that pi is transcendental is not an easy thing. So all of these results came very late, long in the 19th century, using quite advanced mathematical ideas. So let's now move to a different topic, namely alternative tool sets. So of course, classically, we have only the straight edge and the compass, but we can mix this up a bit, right? So what if we allowed compass only? So the question is, what can you construct if you only have a compass and no straight edge? Of course, you can't draw the line anymore, but if we're talking about which points are constructible, the question isn't which figures can you draw, it's just the question of which numbers can you identify on the number line, you know, or which points in the plane can you construct and point at if you only had a compass, you know. And it turns out it's quite shocking, but it's the Moore-Mascheroni theorem, proved first in 1672, that compass-only construction is fully powerful. It's equivalent. Any constructible point that you can construct with straight edge and compass, you can also construct with compass alone. And how would you prove something like that? I mean, you're proving something about all possible construction methods. So what you need to do is something like what we argued with the compass equivalence theorem. You need to argue that anything that you could have done with a straight edge, you can also achieve just with a compass. You know? So for example, suppose we had 2 points and another 2 points, you know, and I'm thinking, you know, I'm thinking of the line. I can't draw the line without the compass, but I'm thinking of the 2 lines that they determine, and I want to construct this point here, you know. And so there's a construction. Given these 2 points, then there's a construction involving a compass only, and it has a couple of dozen circles that you draw. One step in the construction also is to pick a point that's not on either of the lines. So you pick a sort of random point, you build a bunch of circles, and ultimately the construction finds the intersection point here. And so therefore, if you wanted to have intersected 2 lines, then even if you only had a compass, you could still find that intersection point. Okay. So what about the dual situation to that? For example, suppose you have only a straight edge. So it turns out that theorem is also true a little bit. So you need to have at least one circle. So given any circle, so maybe over here on the left, you're given a circle and with a known center and radius. Then if you have a straight edge, you can construct anything that you could construct from a compass and a straight edge. So you only need the straight edge. So you only need one circle, one instance. And the way the proof goes is that you need to argue that anything that you could have done, suppose you were carrying out some construction and over here you would have wanted to draw a big circle. Then using the straight edge, what you do basically is you make similar triangles and bring that picture back over to this circle and do what you wanted to do over here. And then carry using the straight edge only, you can translate it back by the similar triangles to find the corresponding point that you wanted to have over there. And what this theorem, it's an improved version of was known as the rusty compass theorem. Suppose that you had a straight edge and a rusty compass. What's a rusty compass? It's stuck. You can't move it. So a compass is, you know, these 2 pincers, right? But it's rusty, so it's fixed. You can't, the radius of the circles that you can draw is completely fixed. And the point is that it's nevertheless fully powerful. So if you wanted to have drawn a big circle, then, well, the rusty compass says you can only draw that fixed circle size, and then you can do similar triangles and translate. Or one can see that it's a consequence of this other theorem that I was just mentioning, that you just draw one circle with the rusty compass and then you appeal to the other more general theorem. Okay, so what about construction with a marked ruler? So suppose that we have a marked ruler as a straight edge with 2 marks on it, you know, and you can use those marks in your construction by lining them up on lines or points in your figure. And so, for example, with a marked ruler, let's see, suppose you're given a point here, or you're given, say, an angle, okay, like this. Then what you do is you draw a circle of the radius with the mark, you know, so that this is the same as the mark. And then what you do is you take your marked ruler and you hold it so that one point is on here, and you make sure that this distance is the same as that the marks line up both on the circle and the line. You can move the thing around. Of course, if it's really too low, then this distance will be too short. But if it's too high, the distance will be too big. So there's going to be a point in between where you can line up one mark on the circle and one mark on the line, and this one is also on the marked ruler. And then it turns out that this angle is exactly a trisection of this one. In that case, you can prove. So therefore, this is an opposite kind of situation. The marked ruler is more powerful than the straight edge and compass alone. You know, if you have a marked ruler, you can trisect angles, but if all you have is straight edge and compass, you cannot. So it's strictly stronger. So there's some other more fanciful geometric construction methods. So consider origami. This is the Japanese art of paper folding. So you fold the paper, you make beautiful cranes or other exquisite works of art. But we can think of it mathematically. The essence of origami is that you're folding the paper. And of course, that's a fundamentally geometric thing. If we had a figure on the paper and we fold it, then we can see how that figure landed on the other side. And if we think of that as a geometric construction tool, so namely given any line that we're going to fold upon, then given any point on one side, we can construct the image of that point under the reflection. We think of that as a construction method. Or for example, another basic origami fold is given 2 points on the paper, right? You can fold them so as to bring those 2 points together, you know, and then that determines the line. So basically that's allowing you to construct the perpendicular bisector of the line connecting them, right? Because the folding line would be the line that's the perpendicular bisector of the segment joining those original 2 points. Yeah. So the question is, well, how powerful is origami as a construction method? And Robert Gertschlager in 1995 proved that it's equally powerful. This straight edge and compass construction is equivalent to a certain sequence, a certain toolkit of origami folds, 7 fundamental origami folds, and there's reductions in both directions. Anything that origami can do, the straight edge and compass can do, and vice versa. But also there's certain specialized origami folds that are sometimes used in practice that are strictly stronger than that list of 7. So for example, given 2 parabolas, well, so how are you given a parabola? Well, parabola is determined from a point and a vertex line, you know, the set of points equidistant from the line and the point. So if you're given 2 parabolas by means of their focus points and their focal points and their vertex lines, then you can construct a tangent line to a common tangent to the parabolas. Yeah. So in practice, this is something that a skilled origami artist can do. And it turns out that if you allow that construction, then you can construct a cube root of 2. So you can duplicate the cube. And in fact, you can solve any cubic polynomial if you allow that origami fold. Okay, well, let's consider also, say, spirograph constructibility. Maybe when I was a child, I used to play with spirographs, these little plastic rings, gears, and they fit inside each other, and you put the pen in and you make a kind of spiral pattern. And if we think of that as a geometric construction tool, then the question is, what can you construct? And it turns out it's strictly more powerful than classical straight edge and compass constructibility. For example, one of the things you can do is make this spiral picture that has 7 loops in it, and it's perfectly symmetric. And if you look at where those loops intersect, you can make a regular septagon, a 7-sided regular polygon. But that's something that we can prove you cannot construct with straight edge and compass alone. Okay. So now all these different ways of methods of construction lead to the question of what is the ontology of geometry? What are we doing with these geometric constructions? So is geometry, if geometry is meant to be about the nature and features of the sort of ideal geometric figures, points and lines and planes and so on, then it seems like there wouldn't be any reason to object to augmenting the construction toolkit with these other tools, provided that we thought that those tools were according with sound geometrical truth. So if we think there's an objective geometric reality out there that we're trying to understand with our tools, then it would seem there shouldn't be any objection to augmenting our toolkit with these more powerful tools. I mean, do we think that there is a 20-degree angle or not? So if the geometrical reality has a 20-degree angle in it, then maybe we think, well, the straight edge compass isn't powerful enough to tell us the nature of that geometrical reality. And so we should augment those tools with more tools like the marked ruler or some other tools that can construct the 20-degree angle. So, okay, so on the other hand, maybe we think that that the only points that really exist are the ones that we can construct using the classical straight edge and compass tools. This is sort of conservative picture that, well, that's what geometers were using for 2,000 years, and those are the only points that really exist. So if we think about the points that exist in the constructible plane, that's going to satisfy all of Euclid's axioms. And in that plane, there simply are no 20-degree angles, and there are no regular septagons. So it's a different way of thinking what the subject is about. Okay, so on that first way, though, maybe the impossibility proofs are pointing us to realize that there are flaws in our geometric theory. We're missing the axioms that tell us that 20-degree angles exist, and that the cube root of 2 exists, and so on. So we would need to augment the axioms, Euclid's axioms, with axioms that assert that these other kinds of geometric objects exist, because that is not a consequence of Euclid's axioms alone. So we can consider maybe a little more carefully, what is the role of diagrams and figures in a geometric proof, right? Nearly every proof in geometry is accompanied by a figure. Is that figure part of the proof, or is it just a helpful aid? It's often very difficult to understand a proof without that figure, and so it seems like it really is part of the proof. But meanwhile, we also know in certain ways that figures can be misleading. Any specific figure, any figure that we might draw has specific lengths and specific angles. This segment is shorter or longer than that one, even though maybe the hypothesis of the theorem wasn't determining which way it went, but the figure is determining. And so the problem is, or the worry is, that we might make errors in our arguments by looking at the figure and deducing things from the figure because it has a kind of over specificity. Maybe when you do the construction with this particular figure, the certain point that you construct is inside a circle instead of outside, but a different way of setting it up, maybe in a different initial figure would have led it to be outside. And so we're going to be led into error if we're not careful. So I want to show you how that can happen. And so let me just convince you. I'm going to prove that every triangle is isosceles. Okay. Now, of course, this isn't true because we know that there's lots of triangles that aren't isosceles. Isosceles means that two sides have the same length, right? So, but nevertheless, I'm gonna give you an argument. So let's just draw a typical triangle. Okay, here's a triangle, and now pick any point you like and draw the angle bisector. So I'm going to draw the angle bisector. So this angle is the same as this angle, and now think about the opposite side and find the midpoint and draw the perpendicular bisector. Okay, so this is perpendicular. So this is equal to this length here. Okay. And now take this point here and drop perpendiculars to the sides. Okay. And now I've got a triangle here and a triangle here. And they're both right triangles and they have the common angle here. So they're similar, but also they have the same hypotenuse. So they're congruent. So therefore, this length must be congruent to this length, and this length must be congruent to this length. Okay. And now I'm going to draw these lines here from this point to here. Okay. And I'm going to think about this triangle and this one. So here. So they're both right triangles because this was perpendicular by definition. And also this length was equal to this length. Yeah. And the other leg is also common. So therefore, by the Pythagorean theorem, this length must be the same as this length. You know, because it's just leg in a right triangle. The hypotenuse must also be congruent. Okay. And now I think about this triangle and this triangle. You know, they're both right triangles and they have the same hypotenuse and they have a common leg. So therefore the other leg must also be congruent. You know. And so here I've got 2 plus 5 here. And here I've got 2 plus 5 here. And so therefore, the triangle was isosceles. Okay, so I'm not going to tell you the problem with this argument. Of course, it can't be right because not every triangle is isosceles. But it's very difficult to find the flaw in this reasoning. And I can assure you that, in fact, every single step about the triangles, every single step of reasoning about the congruency of the triangles and the angles on the sides and so on, all of that was completely correct. There's no error in the reasoning. I wasn't pulling a fast one on you with reasoning about the triangles. Everything I said about that is correct, but nevertheless, the overall conclusion, there's some kind of subtle flaw in that. And so if you figure it out, I'm going to just leave it here as a puzzle, and please think about it. I'll post a video on YouTube later, and so if you figure it out, just post an answer in the comments there. Okay. It follows, of course, that as a corollary, that every triangle is equilateral. Because if every triangle is isosceles, then, well, we were able to pick which vertex we wanted. So I could have done the same argument with a different vertex, and those two sides should also be equivalent, congruent, and therefore it would actually be an isosceles triangle. Okay, so let's see. Everything takes longer than you think. So let me just talk briefly about this error analysis. So what if we analyze geometric constructions as a kind of, as a process that you would carry out possibly with error, right? So if we think about, say, the Apollonius construction, so we have the line segment AB, and now the first step in that construction was to draw these circles. So we pick B as the center and draw the circle with center A like this, right? But suppose that we don't, when we put the compass down, it's not exactly on A, and so we're going to get maybe slightly different circles depending on exactly how we put. So I can imagine that the possible circles that we might construct is this kind of smudged out kind of shape. And similarly with B, we get a lot of different possible circles that are all very close to one another, but they're not perfect. Okay. And then when we make this intersection, we get this sort of region of possible intersections and possible intersections here. And if we think about all possible lines that we might draw between them, there's actually quite a bit of variation about how the construction would be carried out in practice. And so ultimately, what we're getting is a kind of not just one point for the midpoint, but a kind of whole smeared out region of points that we construct. And if we have this kind of view of the geometric construction as a possibly error prone, maybe the errors are very tiny, but still we're only really constructing with respect to an error. And this would enable us, this kind of perspective would enable us to compare different construction methods as to how accurate they were. Maybe one method is simply better than another in terms of its error, because even if the error values are the same with each step, the first construction maybe is leading to a more precise result, a more accurate result. And this leads to a view maybe of looking at the geometric process itself platonistically. So if the subject is about the Platonic realm of ideal points in the plane, then, well, if we think about the construction procedure itself as a mathematical object, something that could be carried out either imperfectly or perfectly. So we have the imperfect version of the Apollonius construction, but then we have the Platonic ideal, the perfectly performed Apollonius construction. So in the Platonic realm, there's the ideal Apollonius with the flowing white robes, maybe, and taking out his compass and performing the perfectly ideal version of the Apollonius construction to find the perpendicular bisector. So this leads one to take the constructions as mathematical objects subject to analysis. And this is maybe very similar to how we think about computability now, and we'll be talking about that in week 6, I think, computability. Okay, so there's more in the book. So all of these lectures are based on my book. I want to move to the topic of non-Euclidean geometry. So this is maybe one of the most interesting, profound developments in geometry, the discovery of non-Euclidean geometry. And what's at issue here is the parallel postulate. This is the 5th postulate in the Elements, and what it says is the following. So it says, if you have two line segments and you have a transverse, and this angle, and these two angles are adding up to less than a straight angle, then you can extend these lines and find an intersection point. Okay, so given any two line segments, given any two line segments and a transverse, so that these angles are less than a straight angle, then they're going to meet if you extend them far enough. Okay, that's the parallel postulate. There's a different version, Playfair's version of the axiom, and it says that if you have a line and you have a point not on the line, then in the weak form it says there's at most one line through this point which is parallel to the given line, in the sense that it's not intersecting. Okay, the strong version says that there's exactly one line through this point that's parallel to this line. Okay, that's Playfair's formulation. And depending on what the other axioms are, it's equivalent to the parallel postulate. Okay, so of course, this postulate, this axiom, has a fundamentally different character to it than the other axioms. The other axioms say, well, if you have 2 points, then they determine the line. Or if you have a point and another point, then you can make a circle. And so the other axioms are sort of asserting seem to be asserting fundamental truths about the nature of points and lines and circles. But the parallel postulate is this kind of almost technical thing. And the view that mathematicians had for many, many years was that it looks more like it should be a theorem and not an axiom. And so they tried to prove it from the other axioms. They wanted to get rid of this annoying parallel postulate. We wanted just to have it as a theorem. So Euclid, in fact, put off that axiom until the 29th proposition. So he proved 28 propositions using only the other more fundamental axioms. And then he wanted to prove proposition 29, and he needed the parallel postulate. And so he introduced it only at that stage, that late stage. Okay. So at first, of course, people tried just to prove it. But then people had the idea of, well, maybe we should try to prove it by supposing it's false and trying to get a contradiction. So we deny the parallel postulate and then reason from that assumption what happens. And so this is a kind of shift in perspective. And János Bolyai had carried out this process. And he went a long, long way. He derived all kinds of things, all kinds of strange and beautiful mathematical consequences of the violation of the parallel postulate. He never found the contradiction, but what he found developing instead was a beautiful new theory. And it seemed to him to have a kind of internal coherence and a geometric sense that seemed like he would never find a contradiction in that realm. He wrote to his father, and this is 1823, "Out of nothing I have created a strange new universe." So he's sort of discovered non-Euclidean geometry simply by trying to have refute the parallel postulate by contradiction, but instead ended up deriving some of the fundamental facts of non-Euclidean geometry. So Gauss also had been working at the same time, but privately, which is remarkable that he kept it secret. So Gauss had worked out quite a lot of the things that Bolyai had also, but Gauss never published it. I mean, he had planned to publish only posthumously because he said he was fearing the howl of the Boeotians. So it's really quite remarkable for someone of Gauss's stature to be afraid of ridicule. But of course, there was enormous ridicule for working on this parallel postulate because a lot of crank mathematicians would be working on this topic also. Okay, so one of the things that Gauss had wanted to do is he suspected that that in non-Euclidean geometry there might be an absolute notion of scale, a fixed absolute notion of size inherent to the geometry. Euclidean geometry is invariant under scaling, but in non-Euclidean geometry, maybe you could define by some geometrical means an absolute notion of size, which would be of enormous scientific importance if it were true in the physical universe. So if the physical universe were non-Euclidean, we could maybe find that unit, and then we wouldn't need the iron rod in Paris or the platinum rod in Paris. because we could just define the unit length, the meter, say, in terms of this absolute unit of scale that comes from the inherently in the geometry. Okay, so now both Gauss and Bolyai did not have a consistency proof. They just worked out consequences and they seemed to have this coherent theory, but there wasn't any proof that in fact it was coherent. And this didn't come really until Beltrami in 1868. And he was the one who first proved that non-Euclidean geometry is consistent. We can consistently deny the parallel postulate and not be led to contradiction if the original geometry was not contradictory. So I want to show you how to think about that. And I'm going to go over the hour time, I'm sorry. So I want to show you how to think about that. So one way is, so the basic method is to embed non-Euclidean geometry inside Euclidean geometry. So if we assume Euclidean geometry with the parallel postulate, then we want to reinterpret the fundamental notions of point and line and so on in such a way that, so we're going to reinterpret them in Euclidean geometry in such a way that we're going to provide a model for non-Euclidean geometry. So one way of doing that is with what's called spherical geometry. So in spherical geometry, so imagine a sphere. Okay, so maybe here's the equator. Okay, a giant polished silver sphere. We can walk around on it, you know, and of course, on the surface of the sphere, we could do things like carry out Euclidean construction. So if I have a line segment there, I could form the circles and intersect and make a little Apollonius thing, and I could find the perpendicular bisector on the surface of the sphere. I wouldn't notice that it wasn't non-Euclidean, maybe if the sphere was very large. Okay. So in spherical geometry, what we mean by a point is just a point on the surface of the sphere. And now what we mean by a line is a geodesic. So on the surface of the sphere, this is a path that a plane flies when it's flying on the Earth. So it's a great circle. You know, it's a so it's a circle that arises which is coplanar with the center of the sphere. You know, and that is a geodesic because it's locally the path of shortest distance. So any 2 points on such a great circle, it's the shortest distance that connects them locally. That's why planes fly on that path, because it's the shortest distance. So we've redefined a notion of point and line. So a line now in spherical geometry means one of these great circles on the surface. So we think of this sphere as a version of planar geometry. Okay, so when you're on the sphere, you can't look up at the stars and so on. You have only the plane. And when you construct a line with a straight edge, you end up constructing what we can see in the embedded copy is this great circle. Okay. So now the point of this interpretation is that, well, locally we can see the space looks Euclidean. We might not even notice. We can do straight edge and compass constructions on the surface of the sphere. So if they're very tiny, it looks basically Euclidean. But at large scale, we can see that the geometry is totally different from Euclidean geometry. For example, if I start at the North Pole and I go down to the equator, and then I turn and go 1/4 of the way around, and then I turn again and go back up to the North Pole, then, well, this is a right angle because it's going on a longitude line and then on the equator. And this is also a right angle because it was the equator and then a longitude line. But this is also a right angle because we went 1/4 of the way around, you know? And so I've got now a triangle with 3 right angles in it. And this definitely doesn't happen in Euclidean geometry. So it's a way of seeing that the geometrical truths of spherical geometry are somehow different than they are in Euclidean geometry. Okay, also we can see that the parallel postulate is false in spherical geometry because all lines, I mean, sorry, the Euclid version of the parallel postulate is true because all lines intersect, but the Playfair axiom is not true. Because if I have the Playfair axiom says if you have a line and a point on a line, then there should be a line that doesn't intersect the given line. But in this version, all lines intersect. Okay, so it's revealing differences in the in the geometry. So there's a version of this. Okay, the way I describe spherical geometry so far isn't quite fully satisfying all the Euclidean axioms, because some pairs of points have many lines. For example, the North and South Pole don't determine a line. There's many lines that contain the North and South Pole. So one can fix this issue with another interpretation. So we think of the a point now as a pair of opposite points, of antipodal points. So given any pair of opposite points, we think of that as one point in what's called elliptical geometry. So it's another reinterpretation. And in that reinterpretation, you do get all of Euclid's other axioms. So there's another notion of interpreting. So this is hyperbolic space. So if we use the Poincare disk model, we think of the unit circle, the interior of the unit circle, and points are just points in the interior of the unit circle, but lines are now circles that are perpendicular to the boundary. Okay, that's what a line is in hyperbolic space. So if I have such a line and I have a point not on the line, you can see that I can maybe find a lot of points, a lot of lines through this point that don't intersect that one. Yeah. So now if I have here, I can make triangles, and you can see that in hyperbolic space, triangles have angles that add up generally to less than 180 degrees instead of exactly 180. So that's one difference there already. So this is violating Playfair's axiom, because we have many lines through the given point that don't intersect the given line. So the parallel postulate is false in hyperbolic space. So let's talk a little bit about curvature. So if you think about spherical geometry, and you have a point and you make a circle of radius r, so on the surface of the sphere, then because in spherical geometry, so I have a sphere, I have a point, and I make a little radius, and I make the circle of that radius, then the circumference of that circle is a little bit less than you would expect in Euclidean geometry. Of course, in Euclidean geometry, the circumference is 2 pi r, 2 pi times the radius. But because the space is curved, the circumference is a little bit smaller than you would expect. Okay, so this is what it means for a space to be curved. It means that there are slightly fewer points at a given distance from you. Okay, and it's the same in higher dimensions. So for example, in space, if you're standing in three-dimensional space, you could imagine all the points you could reach at arm's length. So that's determining a kind of sphere 1 arm's length away from me, if I move in any direction. And in Euclidean space, that the area of that sphere would be, 4 pi r squared. So that's the area of the points that I can reach at arm's length from me. Okay, but in a positively curved space, it would be less. It would be less than 4 pi r squared, and maybe a lot less if the radius is very big. Okay. Now, hyperbolic space, on the other hand, is negatively curved, which means that if you look at a circle, say in the two-dimensional case, if you look at a circle of a given radius, then the circumference can be bigger than you expect, and much bigger if the space is extremely negatively curved. And similarly, in the three-dimensional version, if you look at all the points that are a given distance from you in hyperbolic space, then there could be many, many more points than you expect. So this is how I write about it. Let's see. If you are a resident of a city in hyperbolic space, then the number of shops and restaurants within a few blocks of your apartment would be enormous, because in hyperbolic space, there are so many more locations that are this close to you. If the space is extremely negatively curved, then there could be whole undiscovered civilizations within walking distance, simply because a strong negative curvature means that there are such a vast number of locations quite nearby. Criminals escape easily in hyperbolic space simply by walking away a short distance. It's too difficult to follow them far, since at any moment one must choose from amongst the so many further directions to continue. For the same reason, you or your loved ones may easily become lost in hyperbolic space, for it is so difficult to find your way exactly back home again. So please be careful and hold them close. Okay, so I want to now turn to the topic of errors in Euclid. So So Euclid is held up as this paragon of deductive reasoning. And the question is, well, how does it fit the bill? And are there mistakes in it? And so, of course, there's some kind of maybe a pedant could object to some minor omissions. For example, he doesn't have an axiom that says there are any points at all, and he doesn't have an axiom saying that every line has at least 2 points on it, or that say not all the points are collinear and so on. So, okay, so we can give him these incidence axioms, right? This sort of non-triviality axiom. But there's other, maybe more serious omissions. So if we think about proposition 1, he's constructing an equilateral triangle. So we have AB. It's just like the Apollonius construction. So he makes a circle centered at B, and he also makes the circle centered at A, and he says therefore they intersect. You know, but let me put an open circle here. You know, why do they intersect? You know, he doesn't have any axiom that says they intersect. This is a missing assumption in his argument. Now, so why is there such a point of intersection? We needed that point to make the perpendicular bisector, right? But maybe the circles somehow pass through each other or something, right? Or maybe you say, well, look, come on, obviously they intersect, right? There's a point there, just, you know, it's where the one circle crosses the other, but it's not, the subject isn't about what's obvious geometrically to us. The subject is about proving things from the axioms. And so if we don't have an axiom that says that there is a point there, then maybe there isn't one. It's a kind of continuity assumption that's really missing. And let me just convince you that there really is something to that. Let's consider the rational plane. So we only have points whose coordinates are both rational numbers. And then given any two rational points, then you can consider the line of all rational points, you know, that the rational points that lie on the line connecting them, and also the rational points on the circle and so on. And this gives a concept of geometry, a sort of geometrical universe, the rational plane universe. And in the rational plane universe, there is no point of intersection there because this is going to have height square root of 3 over 2 if this is distance 1. And the square root of 3 is not a rational point. And so, in fact, in the rational plane, the circles do pass through each other precisely because this point is necessarily irrational. So therefore, we really do need an axiom that says that there should be a point there. And this is a kind of continuity axiom that's present in the axiomatizations of Hilbert and Tarski and so on. They use a version of Dedekind's idea to state a kind of completeness of the geometric figures, and it addresses this flaw in Euclid. Another flaw in Euclid is what could be characterized as the missing concept of between. So Euclid argues with the idea of between quite a lot, but he doesn't have any axioms about it. So, for example, maybe he has a line segment and he has A, B, and C, and he says because B is between A and C, it follows that AB is less than AC, and so on. This kind of reasoning about between. But what is the nature of this betweenness relation? There's no axioms in Euclid about it. But also, let me just convince you, oh, here's another kind of case, another important kind of case. If you have an angle, say, like this, you know, and you make the angle bisector, so this angle is the same as this one, that's possible to construct. Then the question is, does it intersect the line? You know, is there a point here? And you want to say, well, yeah, it does intersect, and also that point is going to be between these two. You know? And so he's using that kind of betweenness idea. But let's think about spherical geometry. So we have these great circles. And think about, say, on the Earth, if we have, say, New York, Sydney, and Prague, they lie approximately on a great circle. So I've got these 3 points, they lie on a line. Which one is between the other? Is Prague between New York and Sydney? Or is Sydney between New York and Prague? Or is New York between Prague and Sydney? How does it go? And if you think about it, you realize, well, it's the concept of between is highly problematic in spherical geometry, that it's not sensible to say that B is between A and C if you can go all the way around. Any of them can be viewed as between the others if you go the other way around, right? Or if you have 2 points, then in Euclidean geometry, we say, well, consider all the points between them. That's the segment. But in spherical geometry, which segment are you talking about? If you have 2 points on a sphere, you could go this way, or you could go the other way. And which one is the segment AB? Which points are the ones that are between A and B? And maybe it's not so clear. Okay, so the other axiomizations of geometry sort of fix this issue. So Hilbert introduces a version of geometry that's explicitly talking about the betweenness relation and the S axioms that say, for example, if B is between A and C, then it's also between C and A, and other axioms of that form. If you have 2 points, B and D, then you can find points A, C, and E, so that B is between A and C is between B and D is between C and E. And okay, so reasoning in this kind of way about betweenness. Tarski also introduced a version called the elementary theory of geometry. So for him, the fundamental objects were just all points, but he had a trinary betweenness relation as a fundamental relation on the points, and also he had an equidistance relation on pairs of points. So this line segment is congruent to that one, and developed geometry using that scheme. Okay, so there is, of course, the connection between geometry and physical space. The question is, for 2,000 years, geometers looked at geometry. The subject of geometry is the study of the mathematical properties of physical space, maybe. But now how does this fit with the sort of Euclidean, non-Euclidean? Suppose that we somehow discover that space is not actually Euclidean, it's non-Euclidean. Would that invalidate Euclid's theorems if we discovered that space isn't actually Euclidean because it, say, doesn't have parallel postulate? So Gauss had wanted to test empirically whether the Euclidean axiom is true or not. You can imagine drawing an enormous triangle. Gauss did it between mountain peaks and got a measurement that was Euclidean to within the accuracy of his measurements. And Lobachevsky called for such experiments to be undertaken at an astronomical scale to determine if the physical universe is Euclidean or not. And so Greenberg emphasizes this point that if you make such a measurement and you have margin of error, then you can show there's sort of several things that could come out of such an experiment. You could conceivably show that space is not Euclidean because you get an angle of, say, 179.5 degrees, and that's far enough away from 180 degrees within your margin of error that you could deduce that space is definitely not Euclidean. But it seems that you couldn't ever establish that space was Euclidean, because if the 180 degrees was within your measurement of error, then there are also some numbers that are very close to 180 that are also within your error of measurement. And so it seems like you can't definitively establish that space is Euclidean, but only that it is not on experimental evidence of that kind. Okay, but none of that really affects the idea of whether a physical observation like that about the physical universe can refute Euclid's theorems. It seems like the hypothetical itself is a refutation of the idea that what geometry is about is the nature of physical space, because we don't think that Euclid's theorems are refuted by any experimental observation at all. We just think that would show physical universe isn't modeled by Euclid's axioms, but it doesn't mean that in Euclidean space the conclusions that Euclid was making aren't still true. So there's this sort of separation between the sort of Platonic ideal of geometrical space and the nature of physical space. And maybe it's easy at first to confuse these two ideas and to think that geometry really is about physical space. But maybe when you think about what the consequences of an experiment would be and so on, you're led to the conclusion that actually the mathematics is about its own ideal Platonic realm, the sort of ideal geometry that it's about, both in the Euclidean and non-Euclidean cases. And then the nature of physical space is just something else. Okay, so I want to conclude by talking about a really remarkable theorem of Tarski and what he proved. I mentioned his axiomization, the elementary theory of geometry. And he proved that that theory is both complete and decidable. So that means that in the language of geometry that he set up, his axiomatization proves or refutes every single statement. Any candidate statement is either a theorem or the negation of a theorem. And furthermore, there's a computable procedure to find out which one. And so this is really amazing because what it shows is it can be viewed as a kind of completion of the subject of geometry. After 2,000 years, we've reduced geometrical reasoning to a rote procedure. We can follow Tarski's procedure to determine the truth of any given geometric statement. I find that really incredible. Let me tell you a little bit about how he did it. It relied on his proof in the real closed field. So if you think about the structure of the real numbers, the real field, then he proved that every statement in the real field as an ordered field is equivalent to a quantifier-free statement, a statement without any quantifiers in it. And for example, just to illustrate, suppose I make a statement, say there is an x, ax squared plus bx plus c equals 0. Okay, this is a statement that has a quantifier in it. And in the real numbers, so a, b, and c are real numbers, then of course this is a quadratic equation, and this statement is saying that it has a solution, but we know exactly when quadratic equations have solutions, it's exactly when the discriminant is positive, is non-negative. B squared minus 4ac should be bigger than or equal to 0. So this is if and only if. So this statement, which has a quantifier, is equivalent to this statement, which doesn't have any quantifier in it. So we've eliminated quantifiers. And what Tarski proved by a quite deep argument in the 1950s is that every statement is equivalent to a quantifier-free statement. And then, because our geometric concepts are expressible in the real numbers, because we can refer to lines and circles and ellipsoids and all of the classic geometric objects by their equations in any dimension, any finite dimension, Tarski's elimination of quantifiers argument shows that we can decide the truth of any geometric statement in any dimension about those kinds of objects. Okay, I find that really incredible, a kind of completion of the subject of geometry. Okay, but of course there's many counter arguments. So one counter argument to that grandiose view is that the procedure takes too long. It's really long. Tarski's original algorithm was the time complexity was not bounded by any elementary recursive function. This has now been improved, and it's double exponential time, which is a dramatic improvement over what he had originally, but it's still infeasible. We can't actually use this algorithm to decide any geometric statement because it would just take too long to answer any interesting question that you write down. It would take the age of the universe to use this algorithm to figure out the answer. And so the algorithm, although it's a theoretical kind of algorithm that works in principle, it's not actually useful for any purpose because we can't wait that long for the answer. Okay, that's all I had to say today. So I'm happy to stick around, and if people want to talk and discuss and ask questions, that's completely fine. So go ahead and ask questions in the chat, or just unmute yourself and ask. That's also fine.
May I ask a question, Professor?
Sure. There's one, though, that came in just on the chat. How does the process of quantifier elimination work in general? So let me just answer that first. So, quantifier elimination is a standard part of the toolkit in model theory, which is a part of mathematical logic. And maybe Tarski's theorem is one of the first most prominent instances of it. I guess, so one can show that certain theories admit quantifier elimination. For example, the theory of dense linear orders. Cantor's argument basically tells you how to, using those ideas of Cantor's categoricity result for endless dense linear orders, you can establish quantifier elimination for that theory. And the theory of algebraically closed fields of characteristic 0 also admits elimination of quantifiers. Generally, those arguments are quite sophisticated and difficult, though. And so when I don't want to, with this example, I don't want to give the impression that somehow that's what Tarski did. His paper is 50 pages long or something like that. And so they're often quite involved reasoning to establish the elimination of quantifiers. But once you get the result, basically, when you can establish elimination of quantifiers result for a theory, it means that you've basically demolished the theory. You completely understand everything about it. Because whenever you do the elimination of quantifiers result, then you're going to get a decision procedure and these other kinds of consequences. So it always comes with this extremely powerful kind of context for understanding what the theory is like when you can establish elimination of quantifiers. Okay, so someone else was asking, was it Ahmed or?
Yes.
Go ahead.
Yes, thank you. I suppose that Euclid knew that the Earth is not flat. I am not sure.
I'm sorry, I didn't quite catch that. He knew that what?
That the Earth is not flat.
Yes, I think so, yeah.
Yeah. So did he have some question about the link between his geometry and the real world? That's my first question. And so the link between theory and empiricism, practical
I see.
question. So that's my first question. The second is that the compass allow us to construct some numbers. We have also the perfect compass, which was made to construct conics and based on the movement. You know? Is there any theory of construction of numbers based on the movement? You know.
I see.
My last question is.
Okay, hang on. We got to give other people a chance. So let me just deal with your questions here. So, so your first question, really, I'm not sure. I mean, this would take a historian. I'm not really a historian, and I don't know what Euclid did or didn't know about whether the Earth was flat or not. I know the ancients. There were some experiments in ancient days that measured the curvature of the Earth quite accurately. Using the length of a shadow at day in cities at different latitudes, and they use that to calculate how big the Earth must be, and it's quite amazing how accurate that calculation was. I mean, to within a few percent, I think. But I think even the classical geometers would separate the idea of the Earth being flat from what they were doing in plane geometry. They would say, well, if the Earth isn't flat, then our planes aren't wrapping around the Earth, but they're going off into space or whatever. And so we're talking about the figures on an actually flat plane. And so I think that they would separate that, although I would defer completely to the historians because I just don't know what they actually knew or wrote about that matter. Your second question, I'm not sure I understand it, but I guess you're talking about conic sections and using them as a method of construction. I guess, okay, this is, of course, if we actually have cones and so on, then we're out of the realm of straight edge and compass, which is in the plane only, right? This is a concept of construction in planar geometry, but when you're doing conic sections, then you have cones, you're already in 3 dimensions. And so you're in a bit of a different realm there already. And I just don't know if those tools are more powerful or not. I tend to think that they're not, because the conics are all quadratics. They're all described by quadratics, and therefore they're not going to bring us out of the degree 2 realm. But meanwhile, any number that's degree of power of 2 over the rationals is constructible, and so therefore my expectation would be that those methods wouldn't bring you outside of what's constructible with straight edge and compass alone. Okay, are there other questions?
Thank you.
Sure, we can come back if other people get a chance. Any other questions or comments? Okay, so if not, then go ahead, Ahmed, if you had a third question.
No, my question was about the perfect compass, which was made by El-Kouhi in the 10th century, and it permits to construct hyperbola and a parabola. And my question is a technical one.
I see.
Is
I don't know enough about it. I'm sorry.
yes, I don't know if there is in England there is some museum where I can find it.
I see. Okay.
Yeah, but,
I know that there's other construction tools which I didn't mention and which aren't in my book, but there's this this hammer one, which is allows you to trisect an angle. So it's really quite remarkable. This sort of hatchet-shaped thing, and you lay it on the figure, and it ends up exactly constructing the trisection. It's really quite amazing. And so there are these kind of tools that you can design that go strictly beyond straight edge and compass constructability. I mean, we already saw several, origami and spirograph and marked ruler and so on, but there's a whole assortment of these tools that are strictly stronger than straight edge and compass. To me, the interesting philosophical question about that is, to what extent are those tools somehow changing our conception of the ontology of geometry, right? If we think that geometry is about this sort of ideal collection of points, then if we're willing to admit these other, if we have that picture of how the ontology of geometry works, then we should be willing to admit these other construction tools. And so why is it that mathematicians were so unwilling to do that for such a long time? Was it because they had the idea that somehow only the points constructible by straight edge and compass were the ones that really existed? Or was it because of some other sort of formal idea in terms of what were they, a person with that point of view, I would want to know, well, what is it that they think the subject of geometry is about? Is it about these sort of ideal points and lines in a plane that may have features that we couldn't achieve? Or maybe it was related to the idea of sort of hope that ultimately straight edge and compass would be as powerful as any of these other tools turned out to be. Okay, we have another question here. Let's see, I can't quite see it. Let me maximize this. Let's see, I can't quite read this. Right, okay, so so the talk, we have these three different concepts of geometry. So first of all, this sort of group action on the power set of some points, or inductive generation of points in a space in terms of construction or axiomatization. So I think that's really quite a good way of describing what some different views that we've talked about are. So this sort of the geometers, the contemporary geometers don't work from construction methods or from axiomatizations, really. They specify what the group of transformations is. And in the Erlangen program, that group of transformations determines what are the geometric concepts, namely any concept that's preserved by that group is a geometric concept, if and only if. And that's quite an abstract picture of what geometry is. Whereas if you think about in terms of construction, then it's fitting much closer with maybe the ancient picture of what's going on in geometry, sort of augmented by these axiomatizations. Okay, so the question was, have you introduced any of these aspects really as a part of some integrated concept of geometry? And I haven't tried to do it, although I guess informally they're all integrated because they're all geometrical. And so these are different facets of geometry and we're trying to tease them apart. So I view the project really differently, not to unify them, but to point out that there are these different ways of looking at what geometry is. That's really what the point of making those distinctions is. Okay. Okay, there's a question here about decidability. So what would you say decidability with theory is what makes mathematicians move on? If Euclidean geometry was not decidable, would mathematicians still be interested in it? Okay, that's really interesting. So, so I remember, okay, so this Tarski's theorem, I just find it incredible. And when I was a postdoc in Berkeley, I taught the logic class there. And I really went overboard with extolling the importance and of Tarski's theorem about the decidability of geometry, and the phrase "geometry is finished" may have been uttered in my lecture. And okay, so then I went back to my office, and it turned out that the very next class taught in that room, and some of the same students, was by Charlie Pugh, who is a famous dynamicist and geometer. And a little while later, after he taught his class, there was a knock on my door, and it was Charlie Pugh. And he was saying, "What is this that you're telling your students that geometry is finished? What is that?" all about. And so we had a really nice discussion about Tarski's theorem, and um, and and it's exactly this point you're making. So if we have a decision procedure for a subject, then does that mean the subject is finished? If you can reduce all questions to a rote procedure in principle, then that's a sense in which we've sort of polished it off, right? Okay, and this was the kind of basis for my enthusiastic remarks. And so one thing I learned from this is that, well, it's sort of surprising to me that oftentimes you can find geometers who don't know about Tarski's theorem, and they don't know that the subject is decidable in principle. And maybe they're surprised to learn it. And I think that's a pity. I think everyone studying geometry should know that there's this decision procedure. Okay, but meanwhile, I think the criticisms of the enthusiasm especially are quite strong. And so I can't be so enthusiastic now because the algorithm is useless. It just takes way too long. It's double exponential time. We might as well not have an algorithm at all if it takes so long that we can't use it to answer any particular question, not even a very tiny question. The algorithm simply isn't going to give us an answer. And so in a sense, we don't have a useful answer. It's a theoretical algorithm only. And so, of course, there's plenty still to do in geometry and open questions, and the geometers are quite busy. But also there's another respect in which that algorithm isn't any good. And that is, it's only working in the very restricted language that Tarski had set up, where you can quantify over points and you can refer to betweenness and to equidistance. And using that, you can make questions like, well, is every conic section that you arise by intersecting this plane and this cone and so on, does it, for any such thing, is there a point such that for the sphere that you construct, blah, 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 like this. So you can make such kind of statements in that language, but what you can't say in that language is any statement that's referring to the integers or to arithmetic or to the possibility of a construction. You can't ask in Tarski's formal language, is there a construction that will achieve this? Or does this construction eventually terminate at a point with a certain property? Those questions are not formalizable in Tarski's language, and they're not subject to the decision procedure. And we know by Gödel's incompleteness theorem, which we're going to talk about in week 7, I think, that it's impossible to have a decision procedure that answers questions about arithmetic, precisely because the incompleteness theorem implies that arithmetic is not decidable. So that's a sense. So those are all senses in which, of course, geometry isn't finished and there's plenty of work to do and plenty of open questions and so on. And there's several ways in which one can object to that decision procedure. And so maybe the existence of the decision procedure doesn't really matter so much in terms of mathematicians leaving the subject. Certainly they're not leaving the subject because of Tarski's theorem. Okay, are there other questions? Right, is the geometric theory that Tarski proved completeness for a first order theory? Yes, his theory is complete. That's what he proved. So the theory is called the elementary theory of geometry, and it's basically the geometry that you get in Cartesian geometry, because it's based on this analysis of the real close field. So it's the geometry that you would be led to if you were thinking of geometric points as represented by real numbers in some fixed dimension, by tuples of real numbers in that dimension. So he has a completeness axiom, and then these betweenness things and so on, and his axiomatization is complete and decidable. I mean, it's a consequence that it's decidable because of the completeness. Of course, whenever you have a complete theory with a computable axiomatizable theory, it will be decidable, because given any question, you can just systematically look through all proofs, and either you're going to find a proof of the statement or you're going to find a proof of the negation, and therefore you will eventually be able to answer yes or no whether that statement is true or not. So decidability is generally a consequence of completeness, and that's how Tarski proved it. Okay, any other comments or questions? All right, so I guess, so that's it for this week then, and I'll see you all next week if you want to come and join us. See you next week. Bye.